Hello everyone, welcome. Good morning, good afternoon, and good evening. Yeah. So welcome to the invited talk section of Asia Quito 2021. It's also the first section of the last day of this conference. Okay, and it is my great pleasure to introduce our speaker, invited speaker of Asia Quito 2021, Professor Yi. Professor Yi is a professor at Shanghai Jiao Tong University. He obtained his Bachelor of Science from Fudan University in 2003, and then his PhD from Nanyang Technological University in 2006. So he has was a postdoctoral research in the UCL Quito group during 2008 and 2010. After returning to China, he worked at East China Normal University from 2011 to 2012 and Tsinghua University for 2012 and 2013. His research interests include side channel analysis and countermeasurement, efficient construction of pseudo-random objects in landing parity with noise. He is a member of Asia Quit Steering Committee and has served on the Program Committee of Asia Quit, Euroquit, Quit, Chess, PKC, and TCC. Okay, let's welcome Professor Yi. Okay, so yeah.
Okay, let me share my slides. Can you see my slides in full screen?
Yeah, it's full screen. Yeah.
I can start. Thank you. Thank you, Hua Xiong, for the introduction and for inviting me and having me here. And it is my great opportunity to talk about our recent works on learning parity with noise. This is a joint work with many people: Chun Guo, Xiangxue Li, Hanling Liu, and Jiang Zhang, and with a bunch of papers published at Crypto 2016, Crypto 2021 this year, and Asia Crypto 2019, and a manuscript that is working in progress. Okay, so the topic is learning parity with noise. The airplane problem is about solving linear congruence in presence of noise, or from the coding theoretic point of view, it's called decoding random linear codes. So the original problem, called the search version, it challenges to find out the secret given the noisy code word, where the secret is uniformly random, and this matrix is also uniformly random and made public. And this noise is a bit complicated. It follows from the coordinate-wise independent distribution, which is called the Bernoulli distribution with noise rate mu. So every individual noise will be equals to 1 with some probability mu, and this mu is parameter. And in cryptography, it is more convenient to use the so-called decisional airplane, where it asks to distinguish the airplane samples from uniform randomness. So these two variants, they are polynomially equivalent. And it is also worth to point out that the noise distribution for the secret is sometimes can be drawn from the noise distribution without compromising the security. And it would be very convenient to use in applications such as public key encryptions. And the airplane comes with many variants based on the noise rate. The standard airplane, the noise rate is constant, meaning that it is independent of the secret size n. And the best known attack is called the BKW, as we show in this slide. It's only like slightly below exponential, right? It's 2 to the n over log n. And when noise is smaller, typically the square root of n, the complexity of the attacks will drop accordingly. But note that a typical hardness assumption is to assume that this problem is polynomially hard. But in many cases, it will be very convenient to be a bit more aggressive to assume that this LPN problem is sub-exponential hard, as long as there is still a significant security gap from the best known attacks. Yeah. And there are also another more extreme case of LPN, which we call extremely low noise LPN, where the hardness assumption is hardness assumed is very close to known attacks. And this is the overview of this presentation and the relevant work. We will show how to construct public key encryption and collision-resistant hash functions from LPN. And there's some like overlapping with the concurrent independent work of Bransky et al. They also show that how to construct collision-resistant hash functions from the extremely low noise LPN, which is highlighted in pink. So another major contribution of Bransky et al. Is that they gave the first worst case to average case reductions for LPN. Namely, they show that the worst case hardness of a decoding problem reduces to the average case hardness of a high noise LPN. And in this talk, we show how to generalize their result to prove the sub-exponential hardness for LPN. And finally, we also report some our latest result on how to do various trade-offs between the time, space, and sample complexities of the BKW without relying on heuristic assumptions. Okay, first we show how to construct the public key encryption and collision-resistant hash functions from LPN. So building PKE and CRH from standard LPN was a long-standing open problem. As you can see, it's mentioned in the Christoph's LPN survey paper in 2012 and Van Diem's LPN survey talk. And we made some progress in solving this problem in the sense that we show how to construct the CRH and PKE from standard LPN with exponential hardness. That means we don't solve this problem completely because we still need the exponential hardness assumption for the standard LPN. Here we briefly recall the definition of PKE. So, where the decryption algorithm must be successful, except with some negligible probability. And there was also some security notions like, CPA security, which is about the computational distinguishability of the ciphertext. And CCA security, where the adversary gets additional access to the decryption oracle, except for the challenge ciphertext, of course. Previously, we know how to construct PKE from a special variant called low noise LPN by Aleknovich at the Fox 2003. So let's take a look. First, Alice would do the key generation. Alice sample LPN samples and keep the secret to herself. And then she send over the public key to Bob. And then Bob, do the encryption with the public key. So he samples another LPN sample, but for the same matrix A, and encrypt the message with the hardcore bit. And then he sent back to the ciphertext to Alice, who decrypts out the message. So the CPA security is simply implied. Actually, trivially follows from the decisional LPN assumption. So, because the public key is actually the LPN samples, and the ciphertext are another instance of the LPN samples, plus the hardcore bit, right? So the security proof is trivial. And here we can analyze the successful probability of the decryption. So we can see that in order to decrypt with high probability, so the noise rate cannot be much greater than the inverse square root of n, right? which is why previous approach to constructing PKE from AirPN needs the low noise. Then before showing our construction, let's discuss what the AirPN assumption we need. It is actually conjectured that the AirPN is hard, even when the secret is arbitrary, as long as it has some non-trivial amount of entropy, like say 2 lambda bits, where lambda is a new parameter. We call this assumption the entropic AirPN, which is we need to construct the PKE. But unfortunately, it's not known to be reducible from the standard AirPN assumption. So here we actually cheated a little bit. So we use a non-uniform matrix, which is actually a product of 2 uniform rectangular matrices, the n by lambda, n and m by lambda dimension the A, and the lambda by n matrix V, right? So this distribution actually can consider as drawn from random subspace of dimension lambda. Right? And then, so if you take a closer look, consider Vx, because V is actually a random matrix. So by the leftover hash lemma, Vx is very statistical close to a very short uniform seed, and therefore, this entropic AirPN assumption here is reducible from a standard AirPN, but only when the AirPN is sufficiently hard. For example, if the entropy parameter lambda is say squared log n, then the standard AirPN needs to be at least sub-exponentially hard. Because this is because the entropic AirPN has much larger dimension than the standard AirPN. So by substituting the value of lambda into this to the lambda squared lambda, we only get like a slightly super polynomial hardness in the security parameter of the entropic AirPN. So then, but then it is sufficient to, then we can show how to construct the PKE from the entropic AirPN, which in turn is implied by the standard sub-exponential hard AirPN, right? So the weak secret now is a random string that has exact Hamming weight log n. So that means that this weak secret has entropy squared log n, right? Because if you take a logarithm of n choose log n, which is just roughly squared log n. So we will set lambda to be squared log n. And then also this entropic AirPN whose noise has constant noise rate, right? Then we just follow the same protocol as Aleknovich's PKE, except we use a different matrix A. We use a very small entropy secret S, and we use constant noise E. Here we highlighted the difference with colors. Like before, the security trivially follows from the entropic AirPN assumption, and the correctness of the scheme is essentially the correlation of a vector that has Hamming weight exactly log n, which is in blue, and another vector that has constant noise, follows the coordinate-wise bandwidth distribution with constant noise rate, which is in yellow. And by piling up lemma, we know that the decryption successful probability is at least noticeable close to uniform. So this is already sufficient to show the feasibility of the construction. Then it's not fully CPA secure PKE yet, but we can add redundancy and use error correction codes to amplify the decryption successful probability, from noticeable to overwhelming. so that we can get a standard CPA secure PKE. And if we want to build a CCA secure airplane-based PKE, we can first build a CCA secure tag-based PKE, and then we transform it into a standard CCA PKE, CCA secure PKE without tags, using the known transforms, known techniques. So here we just omitted the details. So next, we will discuss how to construct the collision-resistant hash functions from RPN. I see already a few. Oh, so you can see my screen, right? Because someone said in the chat that you cannot see the screen.
Yes, I can see it.
I can see it too.
So a cryptographic hash functions maps the messages of arbitrary length to fixed length outputs, right? And there are many security notions like pre-image resistance, second pre-image resistance, and collision resistance, which is the strongest and we care about in this talk. So design a hash function, we typically follow two steps. First, we build a hash function that is length regular, namely it compress fixed length inputs to fixed length outputs with the collision resistant property. And then we extend the domain of this CIH from fixed length to arbitrary length using domain extenders, such as the Merkle-Dangard. Okay. So our construction will look very similar to Altai's sys-based CIH. So let's basically recall the short integer solution assumption, which says that given a random quinary matrix, it is infeasible to find any short solution in terms of L2 distance or L2 or L infinity norm, such that AZ is 0 modular congruent to 0 modular Q, right? So if this assumption is true, then it immediately implies a CIH by itself. Okay, the proof is very straightforward. If we could find a collision for two distinct binary inputs, then the difference of the two inputs constitutes a short solution to the sys problem, right? Since we require the inputs are binary, so their difference, which is a solution, will be short by definition, right? Then here is the technical root of our CIH construction. It looks very similar to the case where we have, LWE can imply sys for certain range of parameters, then sys can in turn imply CIH. But our construction works with binary strings, namely the Q is 2. So we first show that we can construct the CIH from BSVP, binary shortest vector problem, and we show that Airplane can in turn implies BSVP. So similar to the sys problem, there's another problem called in binary case we call it a binary shortest vector problem. Some people say it's not a good BSVP is not a good name, but let's call it a BSVP for now. In the binary case, a short solution means that it is a sparse one, right? Namely, it has very small Hamming weight, right? Or equivalently, in terms of the dual code defined by the matrix A, the problem is to find the short non-zero code word defined by the dual code of A, right? So that's where this name BSVP comes from. Anyway, so our construction follows the construction of CIH from BSVP will follow the so-called expand then compress approach. So in order to use BSVP, the target vector has to be sparse, which is not always guaranteed for arbitrary input. So we need first to apply expanding function that flatten the input to a long but sparse string. And then we multiply this sparse string with the random matrix A. Right? So proof is very similar to the cis-based CIH. So once we have a collision, then the difference of their output will constitute a short solution to BSVP. For that purpose, we require this expanding function to be one-to-one, namely it preserves the distinctiveness. If two distinct input imply two distinct output, so that their difference will be non-zero. Right? And the sparsity of the difference is at most doubled compared to the output of the expanding function. Right? So now it remains to show that how to construct such an expanding function that is one-to-one with a sparse output. There are actually a few proposals on how to construct the spanning function efficiently. For instance, we can divide the input into small blocks of equal length, and we map each block into a sparse selection vector. That is, we view each block as an integer, which specifies the position of the bit 1 in its output. And of course, we set the rest bits to 0. So in this way, we can see that the expanding function enjoys many nice properties. It runs in parallel, which is the way it's defined, and it is sparse and it is injective. Right? So every sub-function, the select SEL, is one-to-one. So is the expanding function, which is just calculate all the sub-functions altogether. So now next, so we just show that the BSVP implies CIH. It then remains to show that the LPN implies BSVP. So we recall that the BSVP aims to find a sparse solution X such that X is 0. And we recall that the decisional LPN is just about distinguish LPN samples from uniform. So the proof, suppose we have a BSVP solver that returns a sparse solution X with good chance. Then we can just multiply it with the string Z to be distinguished. In case that this Z comes from the LPN sample, the output is the inner product between a noise vector essentially and a sparse vector. So they will be biased by the piling up lemma. And in case that this Z is uniformly random and the X is non-zero, then their product will be uniform, just a uniform random bit. And so so we'll be able to use BSVP solver to solve decisional LPN with non-negligible probability. So now we can give the main statement about the LPN implies CIH. So informally, the T-hard LPN assumption implies a square root T-hard CIH, where this lowercase t in red is a tunable parameter with certain degree of freedom. And then we can derive many corollaries from this main theorem, such as the ones shown in this table, such as the second one. Second one is essentially the result of Applebaugh et al. At ITCS. And actually, we can prove an improved version stated as a corollary number one, where we reduce the assumption, hardness assumption of LPN to roughly 2 to the square root of n. And the corollary number 4 is exactly the one given by Branksy et al. At Eurocrypt. And to prove these corollaries, we just set this lowercase t to different values and derive the corresponding hardness parameter capital T for different noise rates. Right. The proof is just very straightforward. But here we have some technical issues which is hidden. Like for the corollary number 2, number 3, and number 4. The matrix dimensions are polynomially related, which is not a problem at all. But for the corollary number 1, we have like a very huge matrix with many like sub-exponential many columns. So this means the construction is not polynomial time computable. But we can actually fix this problem by using another parameter, a new parameter, let's call it lambda. We set lambda to be 2 to the square root of n, such that the function is now polynomial time computable with super polynomial hardness, both in the secret parameter both as a function of the new lambda. But then the input and output is too short, which whose lengths are only polylogarithmic in lambda. But this is not a problem. We can just do a parallel repetition, run sufficiently many copies to make the input and output linear size in lambda, where the collision resistance is preserved under the repetition. Okay, next we introduce how to build more efficient, more parallel domain extenders from the hardness of Airplane. So we know many domain extenders for CIH, like the Merkle-Dangard, which is basically sequential. And when the compression rate is 2, we can use a more parallel mode called the Merkle tree, right? So that to compress for a polynomial compression rate, we only need a logarithmic depth. Next, we are actually more ambitious. So we show that we can come up with a better domain extender under the hardness of Airplane. So one may find that this problem is actually due to the domain extension for positive random generators. Okay, suppose we have a random function that has a small domain, and we want to expand the domain polynomially by a polynomial factor, right? So the best we can hope for is this. So we split the input into many blocks. We tag them with different numbers, and we evaluate the tagged block in parallel with the random function. And then we produce their output XOR sum as output, right? So note that the tagging block is essentially necessary. Otherwise, one could find the trivial collisions by simply permuting the blocks. But now what I can tell you is that this dream version is indeed true. If this R is a random function and assume this Airplane is exponentially hard, then the construction is collision resistant with very nice advantages like polynomial compression rate and maximum parallelizability, since we only evaluate a single layer of random functions plus another layer of XOR gates. Right? But it remains to prove how, or why, and how we can prove this construction, right? But let me say that some people may ask that if you have a random function, then then you trivially get a CIH, right? But this is true. But the problem here, the challenge here is just that we want to build a very parallel mode of compression while preserving the property of collision resistance. So now I'm telling you that we already proved that this dream version is actually collision resistant. So recall that in the previous slide, we show this construction is collision resistant, but the matrix is so huge that the construction cannot be computed in polynomial time in the standard model. But it will be this will be a good thing in the idealized model, right? We simply let the output of the random function corresponding to a column of the random matrix, right? Then we can divide the matrix into many submatrices accordingly, right? And then we recall the instantiation of the expanding function is that it will output many selection vectors, right? Then the output is simply multiplying these submatrices with the corresponding selection vector component-wise, and then output their XOR sum. That is, we essentially prove that the inefficient construction in the standard model, which is corollary number 1, if you can recall in the previous slides, is essentially our dream version of the domain standard in the idealized model with sub-exponential hardness. Okay, so next I will talk about recent works on worst case to average case reduction for AirPin. So we know that as we already said, the AirPin represents the average case problem, namely decoding random linear codes. And its worst case analog is quite obvious, except that the matrix, the vector have not any entropy at all. But we have the promise that the noise vector E has some exact amount of Hamming weight, right? This is just in the average case, in the AirPin problem, we say that the noise vector has the Hamming weight is expected to have weight, some fixed amount of weight. In general, we cannot show a reduction for any code because this code could be a bad code. For example, the generated matrix is just all 0, right? So we can only prove it for a good code, which has some non-trivial amount of minimum Hamming distance. But some previous works, like the work of Branksy et al., consider a stronger version of Hamming distance requirement. Called the balanced code, where the Hamming distance has both upper bound and the lower bound. So in other words, the code words has almost the same number of ones and zeros up to a beta fraction. And in our work, we also consider another code called the independent code, where the generator matrix has k-wise independent rows. MDS code, maximum distance separatable code, MDS code, is a special case of independence code for k equals to n. And we know that the promised NCP is known to be NP hard in the high noise region. And when the noise rate is subconstant, the best known attacks for NCP and AirPin has complexity of roughly 2 to the power of the product of the noise rate and the dimension n. In other words, in the low noise region, we don't know any algorithms that solve the AirPin better than NCP. So next we are going to show how to do worst case to average case reductions for AirPin. So Branksy et al. At Eurocrypt 2019, they give the first worst case to average case reduction from NCP to AirPin. So suppose that we have an NCP instance. So we need to transform the NCP instance into an AirPin sample, right? We can do this by simply multiplying with a sparse random vector R. Right? We're just multiplying this vector in yellow color, right? Then we also need to XOR this message S, because this S is the worst case instance. This S had no entropy at all. We need to XOR this S with another equivalence vector that is uniformly random, right? Of course, we can do this many times to get as many AirPin samples as needed. So Branksy et al. They show a smoothing lemma, which says that for a balanced code C and for a random sparse, where the sparsity of this R is parameterized by D, such that CR concatenated with this XR is statistically close to uniform randomness concatenated with a binary distribution, biased binary distribution, right? So this approach actually works as long as the the underlying binary linear code is balanced code, and R is sampled from some special sparse distribution. They actually prove this through this binary Fourier transform technique. And in our paper, we give a alternative proof using Vazirani's XOR lemma. Actually, these two techniques are equivalent. We just make some simplifications. Now we take a closer look at the BRVW quantitatively. No. First, we look at their smoothing lemma for balanced code. There's some lower bound on the NCP noise rate due to the known attacks. No, otherwise, I mean, so lambda cannot be too small. Otherwise, there will be polynomial time attacks. Right. There's also this GV bound, GV type bound on beta. No, to guarantee that the balanced code we care about indeed exists. Right. Finally, the problem has to this can be seen as a deterministic randomness extraction from a structured source R in presence of leakage XR. Right. So in general, there's a lower bound on the sparsity of the randomness distribution. Right. So D has to be at least n over log n. So under these very strong assumptions, they get very conservative result. Right. Here we can see the range of lambda represent the tension between the assumption and the conclusion. Right. So that means the range of lambda is quite limited. Lambda has to be super constant. Otherwise, there will be polynomial attacks on NCP, falsifying the assumption. And the lambda is upper bounded by O log n at the same time, because any larger lambda would make the LPN noise negligibly close to uniform. So that making the result less meaningful. So typically a typical choice is to set lambda to log n. So we actually observe this. It's very easy to prove that the unconditional case that the CR is statistically close to uniform, but proving the conditional case that the CR is close to uniform given the leakage seems to be very more challenging and less efficient. Since one has to guarantee that it is true for all possibilities of the error X. So what we observe and what we prove is the following. So if R is drawn from a proper distribution that is coordinate-wise independent and sparse, which is essentially the Bernoulli distribution, and then the bond in the conditional case is implied by that of the unconditional case, paying reasonable cost. And we can show this is almost tight. Therefore, it is sufficient to prove that the easy unconditional case for a specific code, such as the balanced code or the independent code we talked about. Right? Actually, we can do a probabilistic analysis and give a very non-constructive form of the smoothing lemma to illustrate the difficulty of proving a meaningful, a more useful smoothing lemma. That is, there exists at least a certain fraction of the code, such that for any error vector of weight W and any sparse distribution, CR is close to uniform given the noise, given the leakage XR. So the proof is just follows 3 steps. The first step is just the leftover hash lemma, right? And then we have the Markov inequality for every error x, there exists a certain fraction that fails the randomness extraction, right? And finally, we can, we have like infinite. We just take into account that we have like at most m choose w different possibilities for the error vector, right? So we can essentially bond summing up to all the fraction of the bad code by a union bond. Okay. So in the end goal is to prove that this hardness for the standard LPN whose noise rate is constant. And we recall that the entropy requirement, then the bad fraction will be much greater than 1. So which means that this analysis is meaningless. Right? Put it differently, it seems that it seems not possible to get a worst case to average case reduction from standard LPN unless more tighter techniques are employed. Right? So, which is the technique we show in the previous slides. Okay. Sorry, it's just what we prove. We reduce the case of the conditional case to that of the unconditional. Sorry, it's running too fast. So this is the tighter technique we talk about, right? The next, okay. So now we can state our main theorem. No, first, this is the main theorem, and we can get a similar result as BRVW in the first as the corollary number 1. Because under when the noise rate of the promised NCP is extremely low, we get standard LPN. We get high. We can show that high noise LPN is hard in the average case. Right? If we compare our results to BRVW quantitatively, you can see that it's actually slightly better. When m, which is polynomial of n, increase, the noise rate of BRVW cease to increase at some point. But for our case, it's always improving when m increases. Okay. So now it comes to our main result. So if the low noise rate NCP problem has almost optimal hardness, namely the best known attacks are almost optimal up to arbitrary polynomial speedup, then it will imply sub-exponential hardness for the standard LPN, meaning that the LPN has constant noise rate. So this is the main result of our work, and proof is quite straightforward. We just based on the theorem, we just substitute the noise rate, the corresponding noise rate, right? And here we can see the end result is a sum of 2 terms. So that's why we have to consider different values for C. Next, I'm going to introduce our recent works on optimizing the BKW algorithm for LPN. So let's basically recall the process of the BKW. Right? So suppose we have a matrix A which is uniformly random, and we have also B which is AS plus E, namely the last column in darker color. The first, if we look at the first B-bit block of the matrix, right, then we can classify and we can divide this matrix into many classes based on the value of the first B block. In fact, we can divide them into like 2 to the B different groups. Within each group, the first B bit of the block is 0. It has the same value, right? Okay. Then we can XOR the first row within each group, within each class. We can XOR the first row with the rest of vectors to cancel out the values of the first block to 0, right? And then we can combine all the resulting vectors all together, right? So that we can get LPN samples with reduced dimension and double the noise, right? But when it comes to the number of samples, we also lose 2 to the B. We also lose 2 to the sorry. To use the pin. We also lose like 2 to the B samples, because we have to, when we do the XOR with the first row, all these first row, they are discarded. So in the end, we will lose 2 to the B samples. And after this iteration, the dimension of the LPN was reduced by B bits, right? So we will get the LPN samples with reduced dimensions and double the noise. But this is only the first iteration. We can do this many iterations. Until in the end, we get only we reduce the dimension to 1. So if you look at the main idea of BKW, it's essentially the problem called the Wagner's generalized birthday problem. So first we find many vectors, say B vectors, that sums to specify the target. For example, the unit vector. Okay, so then this the XOR sum of the corresponding LPN samples, they were corresponding to a candidate for a single secret bit, but only with very mild confidence, right? Because the noise is so huge when they XOR all together. This gives us a good candidate, but only with very small confidence. So then we have to repeat the process many times, and on fresh new samples. Because if you do this on the same samples, then you do the majority voting. There will be correlations among those accumulated noise, right? So overall, if we talk about the complexity of the BKW, if the noise rate is a constant, for instance, Q is like a quarter, then the complexity of the space is roughly 2 to the B. Here we omit polynomial factors. And the time and the sample complexity will be 2 to the B multiplied by 2 to the N over B, 2 to the N over B, right? Here, and this is actually, if we want to minimize the time complexity, we have to set this B to be like N over log N, so that the product of these two terms are roughly of the same order, right? So this is the main idea of BKW. And then actually there remain a few questions, such as if we can do trade-offs between space, time, sample, right? in a way that we do not rely on any heuristics. And question number 2 is that we can, remove the factor. Essentially, if we can remove the second step, right, then we can just save the factor 2 to the n to the 1 over epsilon, right? Although this factor is relatively small compared with the first term, it's actually quite large, right, by itself, because it's quite exponential, sub-exponential, where this epsilon is a small constant, arbitrarily close to 0. So in our manuscript, we presented a tree-structured algorithm framework for optimizing the BKW algorithm. So instead of having a single list, we have many lists, and they are mutually independent. And within each list, we only need each list to consist of to contain pairwise independent vectors. So that means all these lists, they are mutually independent, but each list consists of like two-wise independent vectors. Right? And the rest of the steps are roughly the same as BKW. And then the pairwise independence will preserved from all the leaves all the way down to the root, right? And here our contribution is that this pairwise independence is a very characterization, and it is sufficient to give a non-heuristic analysis of the algorithm with rigorous complexity, time complexity, space complexity, and sample complexity. And in the same time, it enables various trade-offs between sample, time, and space. And in addition, we show that there's no need to repeat the process many times, and therefore we can save this sub-exponential factor. That is, we can once we run this algorithm all the way down to the root, then we can just do the majority voting on this column, right? Then so that we don't need to repeat the process many times on fresh new samples. So with our optimized BKW, we can do time-space trade-offs, where n is time-space complexity of the BKW. Here we introduce this integer c, and we use this c to do the trade-off. When t is 2, then the space and time complexity are the same. When we increase the value of c, we get a larger time, but with a smaller space, right? We can also use the dissection technique to do further optimizations. And we also introduce another parameter beta for further adjustment. Right? In the meantime, we can also use the Grover algorithm to do a quadratic speedup. So in summary, we actually get the same result as et al. From Crypto 2018. But we don't need to rely on any heuristic assumptions. So our optimized BKW can also optimize the time and sample complexity of the BKW algorithm. Right. Here, if we compare with the original BKW or the recent work of Devadas et al. At the TCC 2017, we kind of saving a sub-exponential factor, right? And similar to Ryabashevsky's variant, we can also reduce the sample complexity to, for example, to 2 to the n to the epsilon, where epsilon is a small constant. without, while keeping the time complexity to, disorder, right? This, oh, sorry. So here we can keeping the time complexity at the order of n1, but we use much less samples, right? Or further, we can further push the sample complexity to polynomial, sorry, right. We can further push the time complexity to a polynomial, and compared with the algorithm of Ryabashevsky's approach, we save exponential factor, which is n2, right? Sub-exponential factor. Right? Okay, let me quickly summarize what we have done in this paper, in this talk. First, we show how to construct PKE and CIH from sub-exponential hard standard LPN. And then we show how to do worst case, average case reductions for sub-exponential hard standard LPN. Then we give a non-heuristic approach to do time, space, and sample trade-offs and optimizations for the BKW algorithm. Of course, there remain a few open problems, like if we based on a standard polynomial, standard LPN with polynomial hardness, how to build PKE, CIH, or even FHE and IZK from it, right? Or if it's not possible, why? And we need a better understanding why they are not possible. Right? Okay, that concludes my talk. Thank you for your time, and I will be happy to take questions.
Okay, thank you, Yi, for very inspiring talk. Okay, we have time for common question. From the chat board, if you have any question, you may try to unmute yourself.
I have a question. First of all, thank you for the talk. That was very nice. So on your last slide, you said like you want to the CS open problem. So this is more of a speculative question. Like, what do you think that this would be possible, or do you somehow intuitively feel that it's not possible? It's just an instinctual feeling.
I believe like for PKE, a CIH would be, I believe it's quite negative, right? If you have like standard polynomial hardness LPN, it's quite hard to build a PKE, not even to mention FHE.
Okay. Because, thank you very much.
Thank you for your question.
Any other questions or comments?
So I guess I have one.
Okay.
What about signatures? So of course, since you have CRC, if you have one-way functions, then you have standard construction of signatures. But so can you construct efficient ones, like similar to the cis-based construction that we have for lattices? That, so for example, Fiat-Shamir style constructions, or let's say identification schemes or things like this.
Yeah, like you said, it's a very good question. Like you said, you can do it from the generic transforms from one-way function. But if we want to do like cis-based, I don't know. Which we made some attempts, but it doesn't work out. Like if you want to do rejection sampling, then on the binary field, it's not possible. It's seemingly not possible. Just I don't know. My guess is quite negative. Maybe very maybe negative. Negative. I don't know.
Thank you very much.
Thank you.
Okay, good. We have one from the chat board. So can you see it? Can we?
I don't. I don't
okay.
know.
Okay. Can we interpret the PKE from code-based assumptions, and what are the advantages of this PKE over MACDIS equations?
Oh, it's, we don't think we have advantage over McAlice because you know, in this case we just you know, it shows the feasibility, but in this case then the security, we actually like, you know, we do some trade-off. You know, we lose, we use very strong assumptions like sub-exponential hardness only to get, you know, quasi-polynomial secure PKE. So that will be not practical. If we want a more practical PKE, we can go for Aleknovich's PKE. And then, but in that case, I don't think Aleknovich's PKE is still not efficient enough to compare with McAlice. So
Okay,
it's
good.
theoretical.
Yeah. Okay, thank you. Yeah, I guess we run out of time now. Yeah, we probably you have other question or comment you might post on the chat room. Okay, so we thank you again for for the talk, and we close this section and come back in half hour. Yeah.
Thank you for inviting me.